I start KWIX presentation and I introduce the CMOS compatible synaptic transistor created by T-person electrolyte tantalum oxide hybrid electric double layer. Here's our content and I start presentation. Neuromorphic computing system is inspired by the human brain and it has lots of advantages such as ultra low power consumption, real-time processing of unstructured sensory data, touch and validation tolerance, self-learning and adaptive to changing environment. And each system has been investigated to replace traditional phone Neumann architecture. And it can also combine information and storage at the same time. To realize biological synapse, two terminal memory stars are proposed for artificial synapse. But the cross-point array of memory stars are suppressed by the leakage current and excessive noise. In contrast, three-terminal synaptic devices are more appropriate for synaptic devices. When a voltage stimulus is applied to the gate electrode, the channel conductance is modulated. We studied the three-terminal synaptic transistor with T-person electrolyte. T-person electrolyte has some advantages such as abundant, inexpensive, non-toxic, biocompatible, and it has high transparency and flexibility. Also, it has high capacitance for photonic mobile ion. Here is electric double layer. Electric double layer has extremely large capacitance and it has high organic carrier density. So it acts as like a nano gas capacitor. The electric double layer without tantalum oxide undergoes swelling or outgassing problems during the baking or photolithography process. But the EDL with tantalum oxide was well prepared without outgassing or swelling problems. Accordingly, tantalum oxide acts as an effective barrier to prevent deformation of organic layer, and it ensures a stable CMOS patterning process. Also, tantalum oxide is high K dielectric, so its capacitance is high. To make a device, we use speed coating to photoresist coating. And then we use convection oven for baking the sample. And also we use RF monochrome sputtering to deposit the EGS channel and tantalum dielectric. Here is fabrication flow. First, prepare a T-person solution and then cleaned with RCA cleaning. To make a neurotransmitter layer, we spin coat the T-person solution and bake the sample. The 80 nanometer tantalum oxide and 50 nanometer EGS channel are deposited on the T-person electrolyte by using RF magnetron sputtering system. Active patterning of the EGS channel are performed by using positive photolithography and wet etching. Finally, 100 nanometer titanium source drain electrodes are deposited by using E-beam evaporator and patterning by lift-off method. Here is our result, and first is electrical property. Figure A shows the transport characteristic of the hybrid EDL. As we can see, here is hysteresis window. The drain current are measured by pure switch mode, and threshold voltage was obtained by extrapolating the linear curve of the transfer characteristic. Figure B shows the output characteristic. At the low drain voltage region, it indicates the ohmic contact between EGS channel and titanium source drain electrode. As the drain voltage increases, drain current saturated and exceeded a pinch. We connected the resistor in series for inverting operation. Figure A shows the British curve and figure B shows the dynamic inverting response. When input voltage is low, the EDLT is off state and output voltage is high. In contrast, input voltage is high, the EDLT is on state and output voltage is relatively low. Figure B shows the dynamic inverting response. We use 4 Hz frequency and square wave. The inverting response are well prepared and it will respond by low input voltage. Here is synaptic operation. Figure A shows the changes in counterclockwise hysteresis of according to the gate voltage sweep range. And figure B shows the threshold voltage and hysteresis window. As the maximum gate voltage increases 0 to 5 volt, the threshold voltage remain constantly, but the hysteresis window increase linearly. It is related to the polarization of the dipoles in the tantalum oxide high-K dielectric and the migration of the mobile ions in tithosan electrolyte. Induced charge carriers at the interface of the Ig channel and the hybrid ETL. The last is EPSC response and decay. The upper figure shows the EPSC response according to the number of spikes. When a single spike is applied to the gate, the EPSC reaches a peak level, almost 140 nanoampere, and then it rapidly decays in a millisecond. This short EPSC duration represents short-term potentiation. When multiple spikes are applied to the gate, the magnitude of the EPSC steadily increases with the number of spikes. And the bottom figure shows the decay of the EPSC after the spike stimulus over time with respect to the number of spike pulses. We can determine it that the EPSC increases as the number of gate pulses increase. This long EPSC duration time represents the long-term potentiation. Here is our conclusion. Total lithography and etching process on the organic tithosan electrolyte were successfully conducted through stacking the tantalum oxide high-K dielectric. The on-off current ratio, threshold voltage, sub-threshold swing, and stereo mobility balance of the tithosan electrolyte tantalum oxide hybrid EDLT were here. An overall voltage transition in VTC and good dynamic inverting action to the low power square wave input signals for the resistor loaded inverter circuit. EPSC is modulated by the presynaptic stimulus numbers and increased portion of the STP and LTP by the increased stimulus number. The EDLT gated by the tithosan electrolyte tantalum oxide hybrid EDL is expected to provide compact neural architecture system. Thank you.